horizontally projected motions, projected objects. I'll read it, but if you want to write down the important stuff or the whole thing, you can. But I'll read it slowly if you want to write. And this is a very good problem because, again, it's applicable. This is a real-life situation. This stuff happens. A C-130J Super Hercules plane, which is a cargo plane that the Air Force uses, okay, flying 500 meters above the ground, needs to drop a package to soldiers located on a remote island. Okay? So we have a plane flying overhead, and it needs to drop a package so that it will land on the island so that the soldiers can use the utilities or the materials inside of the package. Now, they're not going to land. That's the whole thing here. They do this a lot. They drop them with either parachutes, or sometimes they'll drop them without parachutes, but they're able to land and bounce. Okay? Like a care package. Yes, very good. Now, if the velocity of the plane, and this is the actual velocity, is 670 kilometers per hour, which I converted for you to 186 meters per second, when it drops the package, how far will the package travel horizontally before it hits the island? And how long will it take to reach the island or reach ground level? Okay? I'll draw an image and we'll get an idea of what it looks like. But again, plane flying overhead, 500 meters above. It's traveling, the plane is traveling at 186 meters per second when it drops the package. How far will the package travel horizontally, and how long will it take for it to land? Okay, how long will it take for it to land? Again, drawing things really does help. Okay? So I'm going to draw a quick airplane over here. Okay, the airplane is traveling in this direction. The airplane's velocity is 186 meters per second. We know that the airplane is above the ground, but we know that here is all water. And we've got this island here, and then we've got more water. We're told the distance above ground of the airplane is 500 meters.
We won't have to convert it, right?
I gave you the conversion again. It was given as 670, but I wrote 186 there. Okay? If you're given something like this and you need to convert in the test, you can just use the app. But for the most part, for these, I'm going to give them to you like that. Because testing conversions is not really what this test is about. There's no use losing points to that. All right, so we got an island. We've got this plane traveling. We want to know, once the package is dropped, so let's draw the package in red, say it's a first aid package. The package is dropped, and think about this logically. If you were in a car and you throw something out the window, it doesn't just stop. The object would continue to move with you, but it would eventually fall to the ground. So this object is not going to fall straight down, right? There's a game that Jeff brought up called something Monkeys on an iPhone now. Anybody know what I'm talking about? Where you're like a monkey and you have to like fly and drop like bombs on things?
I don't think yes.
Has anyone seen this? I it up. It made sense though. So in the game, he said, you know, you're a monkey and you have to like, a monkey, and you're like flying from tree to tree, and you have to drop like what look like water balloons on objects. Now when you drop the water balloon, it doesn't fall straight down because the monkey's flying or swinging. And when he drops it, the monkey's swinging and then it falls off like this. It's the same idea. This package is going to fall like this. Okay, it's going to be dropped here, but it's got some velocity. So it's going to move like that Tom Cruise example from yesterday when he ran off the bridge and his motion looked like this. It's the same problem really. Because again, remember, in a car, if you're sitting in the car and the car is traveling at 50 miles an hour, so are you, right? Because you're moving with the car. So if you jump out of the car, you're still traveling 50 miles an hour, you're going to slow down once you hit the ground and start tumbling. So this package, its velocity is the same as the plane's velocity. So they give us the plane's velocity, but we need to make sure that we understand that the velocity of this package is completely horizontal, and its component, or its magnitude, is 186 meters per second. Chance.
So initial velocity and final velocity don't matter for the horizontal?
Good. Why not from yesterday? Remember, why from yesterday is there no difference between the initial and the final in the x direction? Sure?
Because there's no acceleration.
Very good. That's it right there. Remember, the acceleration in the x direction is always 0. There is nothing propelling this package. If there was like a rocket booster behind the package, and after it was dropped, it like launched it forward, like a torpedo in a submarine, when it gets dropped in, it has a little, a propulsion system, that would be acceleration in the x. But these problems don't have that involved in them. not going to have those involved in. We can do them, they're a little more complicated though. Okay, to make the problem a lot tougher.
Acceleration is always constant with a horizontal projection.
Velocity, you mean, velocity,
Right,
yes,
and then
velocity.
acceleration is always zero.
Acceleration is always zero, and when there's no acceleration, think about a car. When you're not accelerating, it's like you're on cruise control, right? You hit cruise control, there's no acceleration, you just coast the whole way. You're just going to coast the whole way. Okay? So, the initial velocity of this package is the same throughout the whole path, 186. Okay? So what are we trying to find in this problem? What are we trying to find? Time, good.
And
In which direction?
No, you gotta
Read the word before displacement.
Oh,
Or
horizontal.
not before displacement, but right? Yeah, there it is. See that?
what does that mean?
How far will the package travel horizontally? So when we look for displacement here, Kareem, we're looking for delta x, or just x, okay? Again, we know the y value. The y value is negative 500 because it falls 500 down, right? This object is going to fall 500 meters downward. And I should really go like this, by the way, to be really specific, right? Because it's from the package length, really. So it's going to fall 500 meters, but we want to know how far is this distance. Why do I care about that distance, realistically? Forget math and physics. Think about this problem, really. Why would the pilot care about what this distance is? Chance.
So it's not too far out of reach of the source.
Yeah. If he drops it too early, what's going to happen? The package is going to land.
In the water.
If he drops it too late, it's going to land in the water. So we have this like landing zone here. And realistically, there's a little room for error, right? Because the island might be like what? 30 meters across, right? 30 meters? So,
Stop.
guys, if this island is 30 meters across, there's room for error, right? It can land here, it can land here, 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 but we're not really accounting for that room for error right now. We're just saying, what is delta x going to be? Okay? So keep that in mind. There's room for error. There's room for error. It's like a factor of safety. Why do I care about the time in this problem? Why do I care about the time?
I don't. Then you know exactly what point, like how long it's going to take.
Well, it doesn't matter.
Because
You answered the question, what is time? So I'm saying, why do I care about time?
because it goes like hand in hand with displacement, right?
It definitely does.
At that point, you're going to be at that displacement, and then that's when you drop it at that time.
Close.
And how long it will take to get there.
That's the key. How long will it take to get there? Why is that important? Why is it important how long it will take to land? Erica was pointing to the side.
Oh, you're pointing.
Yeah.
Okay. Because you're trying to figure out like the horizontal, you know what I'm trying to say. But if it goes to the same thing with like if you drop too early, it's gonna go in the water, so you have to time it out.
Yes, absolutely, absolutely. But there's other reasons. Why else is it important how long it takes? Yes, again, same thing she said. They're going to couple.
So no one gets whacked in the head with a package and on
The plane's still moving.
Things moving short.
Well,
Are the soldiers going to wait there all day for this package?
That's what I said. So no one gets like.
Yeah.
I
Like,
mean, they shouldn't really be that antsy. We're trying to be nice and give them a good
Yeah.
Aaron?
they need to know.
Sorry, that
what's
was
gonna be
toothpaste.
Yeah, that's it.
there.
They need to know, guys, they need to know when it's going to be there. So if the pilot says this, if the pilot says, I'm going to drop the package at 2:35, and say it takes 5 minutes to land, they need to know to be there at 2:40 to get it. Agreed?
Yeah.
So the time matters. It makes sense.
Well, it's not like anyone's about to shoot them, so they can think they're.
How do you know? What if they're like guerrilla warfare in the jungle on this island? We don't know. You never know.
I don't know.
Then the opposing side
That's
can
what I'm saying,
steal their care
hypothetically, right?
package.
Is there a parachute on this package?
There's not. There's not a parachute.
Can it break yet?
No, it's cushion. It's cushion.
You were just making stuff up.
Yeah, you are really just falling into the details.
Because if I put a parachute, right? Listen. If I put a parachute,
Then
the
they're for
acceleration, the
It's
acceleration is not negative 9.81 anymore. It takes
Oh.
longer to drop, and we wouldn't know what the acceleration is. So for this problem, we have to say there's no parachute.
Mr. Howell, I'm gonna go skydiving.
Make believe there's like springs all on the outside of it. So when it lands, it just bounces a little bit. Okay?
So physics, they were great.
You know skydiving?
Yeah, me and my dad
We're
got
gonna do it.
great.
You gotta get a video of it. Do the video.
Yeah.
You know what I'm saying?
Yeah,
If
like
you see
they
what the video
videotaped
is
it.
all the way down. And then show it.
Okay, that you would be so sick of that after about
If you
2
show it, we
months.
can figure out the physics
Do you
behind
wanna
it.
come
Let's focus. AY, good. Negative 9.81. What's AY?
Acceleration in the y direction.
Vertical acceleration. AX was horizontal acceleration. Remember, this is just gravity. AY is just G, little g, gravity.
That's for the free fall, right?
Correct, but it technically is free falling, remember? Because the object is launched horizontally in the vertical direction. It's like a free fall. Remember the tennis balls?
So we have two
Oh, we
acceleration?
remember what?
Yes, in the X, because we're going to make that column. Remember yesterday?
Oh,
Think back to yesterday, okay? All right, let's write this
I
one.
had a projectile vomit at two rears going way.
I love how you guys forget you're being recorded all the time.
I don't do anything.
So, in the X direction, we're trying to figure out what this quantity is. Okay? We know that the velocity initially in the X, which is constant the whole time, in the X
Oh, sorry.
is 186. You jumped the gun there. We don't know what the time is either. That's my X direction. And the acceleration is already 0.
Wait.
So right away, see how many variables are missing here? So we probably can't do much with this side yet, right?
Yeah.
Okay, everybody see that? Can't do too much on this side just yet. On this side now. What is the value for the displacement vertically?
500.
What kind of sign should it be, guys? Come on. Negative. Units are meters, but the sign is negative. Why is that funny?
Wait, why? Is it really displacement?
Remember, X and Y are both displacements. Now we just specified this is horizontal, this is vertical.
so the AY is negative 9.1.
Good, we got that done already?
Wait, why? If we need to find out.
Because it's always
Vertical,
that's a constant.
vertical acceleration is always negative
0.81.
This is horizontal.
No,
Oh, why? Okay.
Why?
Wait, so why is it?
AX never has anything.
Y is the vertical, like your y-axis. Think about your axes, guys. Use your axes. Y is vertical.
Sorry.
It's all right. Time is unknown still. Here's the question we need to figure out. There's some sort of initial velocity in the y direction. Why is it 0 here?
Because it was not moving until you
One
pushed
at
it
a
off.
time, one at a time. Helen.
It was not moving until you pushed it off the thing.
Okay.
It started at 0 until it got
You didn't throw it, really. You didn't throw it horizontally.
You didn't give it any additional push horizontally.
Yeah, it was just dropped. Remember? Guys, watch. Here's the plane. The plane is flying by. The plane is flying by. And I'm gonna actually illustrate this. Plane, the plane drops it. Notice, it's dropping straight down and then this way, alright? So it's like a free fall, like the tennis ball yesterday. When the one ball was dropped and the other one was rolled up the table, they still landed at the same time because their initial velocity in the vertical direction is 0. Okay? So when I move and the plane is about to drop an object, the plane only has horizontal velocity. So when it's dropped like it's from rest. So VIY is always going to be 0 when it's horizontally launched. Okay? When it's horizontally launched, it's going to be 0. But initially it's not, remember? The plane is going horizontal first. It drops it, it goes horizontal for a split second, then begins to go at an angle. Tomorrow, we're going to look at objects that are launched from the ground at an angle initially. And that's when we have to break it into its components.
Sorry, where did we get 186?
186 was given, it was the speed, and we converted it from kilometers per hour.
It's a speed.
It was given in kilometers per hour, and that's the conversion. All right. So with this information, clearly the left-hand side. If I have no acceleration from yesterday, who remembers what formula was always used in the X direction? It's a given. You're always going to use a certain formula here when there's no acceleration. Erica, is that a half hand or is it a full hand?
I think it's a full hand.
You want Tristan to answer first?
Yeah.
Oh, X is equal to VI plus.
That's not it.
No.
No. Erica?
Is it,
E equals X over T.
Good. Again, 0 acceleration. That's what we learned in section 2.1. This was the story equation we have from section 2.1 when there's no acceleration. Whenever there's no acceleration, velocity is displacement over time.
Hold on, but we don't
Okay.
have the.
That's why you have to solve for.
That's why we have to figure out something else here. Because again, look, we know V, but we don't know X or T. So we got to solve for something over here and then move it over here.
Let's solve
That's
for
only
T.
we're gonna solve for T.
Good. Because T is our what variable? We call it yesterday?
Oh, it's the constant.
It,
no.
Oh,
it's a good. What's that called though? I called it something yesterday. Helen's right. T is the same in both directions, for sure. So if I find T here, right here, if I find T, I can take that T, plug it in. Then I'll know T, I know V, I can find X. What is it called when the variable works in both directions?
Interchangeable.
Interchangeable, good, but I called it
So
the linking variable yesterday. Linking. Linking.
Wait, I'm really confused.
Okay?
Why do you need to find X?
Because right now, we're trying to find X in the problem. That's what we were looking for. And we're trying to find time. But all I know is V over here. So I can't find these because there's two variables. We don't know them. So if I can find T over here, I can then plug it in over here.
So it's really
And
gonna
then I'll know these two, and then I can find the X value. Okay? I saw a hand. Thank you.
So you use the equation when there's no acceleration for X.
Correct.
Can you use
Correct.
it for Y?
No, because there's acceleration.
Oh, okay.
Remember, when there's
No,
acceleration,
I mean if there's no acceleration in the Y.
sure, sure. But when there is acceleration, there always is in the Y, actually, Erica, because it's gravity. Gravity doesn't go away.
Right, okay.
Okay? So we're always going to use one of our three kinematic equations over here. Steph, did you have a question? You're good.
No, never mind. I was
Okay.
just talking to someone.
What do we got? Helen.
The VIY times T.
Good.
Equal, plus 1/2 AY times T. T squared times T squared.
Okay? Again, why am I using this equation? Well, let's go through the process. We know VIY. It's right here. We know acceleration. It's here. We know the Y value. It's up at the top. It's kind of got crossed off -500. So we can find time. Now, it looks like this equation is tough because we have T squared and we have T. But what happens to the VIT part? It goes off because VI is 0. So that whole thing drops off, which makes this equation much simpler. Okay, it makes the equation a lot easier.
So they just plug in the negative 9.81.
We know this is -500 on the left, 1/2 of -9.81. I'm dropping units, by the way. Okay, again, where did I get 500? Look at the diagram, right? Given as the vertical displacement, yes.
Get the answer.
Solving for T. Check please what you get. Make sure you get this number. Helen, what do you got?
Oh, I didn't get it yet, but
Okay.
I was gonna say.
Go ahead. You should get 10.09. Please check that you do.
Can you go through solving it?
I'm sorry?
What are you doing? You're distributing, doing all the numbers, blah, blah, blah.
All right. I'm sorry, I'm not frustrated, but guys, this is Algebra 1. We need to be able to do this ourselves. I can't stop. I'm going to show you once. Remember how to do this. Here, this is 1/2. If I want to get rid of 1/2, what do I do?
Times 2.
Times 2. So make this -1,000 over here, and it'll drop it. So far, so good? Okay, again, multiply by 2, multiply by 2. Cancel, cancel. How do you get rid of the -9.81? Divide because it's currently being multiplied. So I divide by -9.81. Negative, negative yields some positive number. Oops. Some positive number. I don't even have that step written down because I just do it all in one step. You're going to get some value here around 100. 100 and change. What is the actual number here when you divide these two people? Again, I did it all in one step. Hunter? Thank you. Now, how do I get rid of the square? Square root it. Okay? So the square root of both sides, we're going to get time equals 10.09 seconds. Why do I not care about the negative root in this case? Why don't I put a plus or minus on the outside?
Wait, why did you
Because it's time. Can time be negative? No, time can't be negative, okay? Again, I would normally put a plus or minus out here, but it doesn't matter because it's time. So the time is 10 seconds. That's the time it takes once the object is dropped. Now, realistically, they probably put a parachute on this thing, right? Like was asked earlier?
Yeah.
Okay, so it probably take more than 10 seconds to land. Now, if we know it's 10.09, go back up here. We know this is 186. We can say x over 10.09 now. See that? Again, the velocity was 186. We know now the time is 10.09. From the y direction we found the time. So we plug it in the x direction, and now we can find that horizontal displacement. Okay? So bring the 10.09 out by what operation?
multiplication?
Multiplication. When you multiply 10.09 times 186,
1,876.74.
76 problem?
Meters per second.
Oh, people. Displacement is only meters. We're looking for the horizontal displacement. You measure it as a length. Length is measured in meters, please.
So that's it?
Okay? So this guy that's driving the plane, or flying the plane, needs to know when he's about 1,877 miles or meters from the island to drop it. That make sense? Okay? And they'll have a little thing, and it'll say like, and this is actually how they do it. They have like a little homing device, or an like you know the detector from yesterday. He uses some sort of a signal to find the distance between them, and it'll know exactly when to drop the object. Okay? What time is the period over? 2:29?
Yeah.
Dang, man, that went fast.
Wait, what did we do?
Yeah, we were late.
Okay, let's start at the beginning of a different one.
In 5 minutes?
Start is the key word. Start is the key word.
Okay, good.
Now, let's say we have a problem where, okay, got it. Let's say we have a problem where we have a cliff, but the height of the cliff is unknown. We're going to go right into the diagram here. I'm making this one up. We have the height of a cliff, but the height of the cliff is unknown. And I'm going to call it h. It's y, but you're going to see h for height a lot. But we know that that's y, okay? Even though you see h there, I'm just trying to get you familiar with it, because diagrams use h a lot, because they talk about the height of a cliff. But that is your y value. Now, the height is unknown. We have an object launched horizontally. Again, we're only doing horizontal motion. Ignore that little lip there. Horizontal motion. We know the velocity of the object when it's launched is 20 meters per second. We are told that throughout its path, it covers a horizontal displacement of 100 meters. Right? And the question says to find the height of the cliff. That's all you know. You know the initial velocity in the horizontal direction is 20. You know that the displacement covered is 100 meters, and you want to find the height of the cliff. Everybody have the diagram drawn?
Yeah.
Okay, let's go into our x and y quickly. In the x direction, we're not giving anything about time yet, nope. In the x direction, what do I actually know here? What do I know in the x direction?
100 meters.
Good, Gabby. What else, Gabby? What else do you know?
We know
Dx
that.
equals 20.
Gabby, come on. I know you know, Kareem, but I asked her. Okay, again, we know these two facts in the x, don't we?
Yeah.
Okay, do we know time? So
No.
leave it blank, but we can find time very easily in the x.
Acceleration.
Acceleration is always
0.
good. In the y direction now. In the y direction, do I know the y, the height?
No.
Do I know the acceleration?
Yes.
-9.
0.81 meters.
Well done. What's the initial velocity in the y always for these problems? Good. Because again, it's launched horizontally. Do I know the time?
No.
All right, so take a look. If I want to find the value of y, remember I want to find the height of the cliff. I want to find y. To get y, though, I need to get t. So what should we do on this hand side, or this left-hand side?
Fine, too.
Find the time. Send me through, Steph.
You set it up v equals x over t,
Good.
which is 20 meters per second equals 100 meters
Over t.
over t.
Now we take those and flip-flop, right? Remember this? We switch the positions of the t and the 20 to solve this equation.
So you get 5 seconds per t.
Good. So the time it takes for this object to land is 5 seconds. Go to your y side, or your y, whatever, your y side of the equation. You know our formula. Do I care about the VI part? Why not? Good, it's 0, drops off. If I want to find y, I just plug in now. And remember, the time is the linking variable. From the other side, we take that time of 5 and plug it in here. Okay? We're going to check out what our numbers come out to be. I got a follow-up question for you. You can multiply that on your own. You can do that. Now, follow-up question. If I want to find the final velocity of the object in the y direction, give me one more second. The final velocity in the y direction, you can use either of these equations.
To find the final velocity.
Watch. In the y direction, remember these two equations here? We know the initial velocity is 0 no matter what. So whether we use either equation, it's going to drop off. In the y direction. In the y direction, the acceleration is negative 9.81 here or here. If I want to use x, though, what do I have to make x instead since we're in the y direction? Y. And the y value is whatever you got from this answer right here. You can plug that in to get your vf squared, then take the square root. Or you can just plug in the time of 5 seconds, do 5 times negative 9.81 to get the final velocity.
Was that important? I
Okay.
don't really understand that.
Yeah, that one.
We can pick up with that one tomorrow. Estimate, thank you. Tonight, your homework's on Moodle, but if you want to write it down, you can. It's page 102, numbers 3 and 4. Okay? It's on Moodle, but you're welcome to look and write it down now.